Okay, continuing with the activation energy. So another term that maybe you just encounter. So molecule are said to possess a minimum amount of energy to react. So they must have a certain amount of energy for them to produce the product. Okay, you notice some reaction will require to supply some heat. Maybe you have to heat the reaction at 60 degrees Celsius or maybe 70 degrees Celsius. So that is one way on how the energy is being supplied. So in order to form this product, bond must be broken in the reactants, and to break this bond, it will requires energy. Okay, and the amount energy depends on the type of bonds between the reactants. If you have covalent bonds, then the amount of energy required to break it is even higher, okay, compared to like polar bonds. So molecules moving too slowly, okay, with too little kinetic energy, don't react when they collide with each other. So it's like that's why this all of these reactant requires a certain amount of energy for them to collide in order to produce the product intended. So activation energy is the minimum energy required to initiate a chemical reaction. Okay, so this is the definition for activation energy, and the values of EA will differs for every reaction. Okay, EA will vary with the types of reactions that you are doing. So this guy is this girls actually is playing a golf. So she's trying to hit the golf ball across this so-called like uh, tiny hill over here. Okay, this tiny hill. So in order for the balls to go over the hill, so there must be a minimum amount of energy to hit for she to hit the ball so that the balls can pass this highest top and then move over to this side. So that is another way how activation energy can be explained. Let's say using this example of the rearrangement reaction for methyl isonitrile. So the starting material is having the carbon bonded to the nitrogen, which is this way, and then the product you have CC bond, okay, instead of the carbon bonded to nitrogen. So in the middle over here, we have what we call as the intermediate, okay, intermediate. So in CH3N triple bond C, the CN triple bond C bond will bend until this bond breaks, and then the NC proportion is perpendicular to the CH3 portion. So first this will break, okay, and then it will become perpendicular, which is 90 degrees, okay. So this structure is called the activated complex, or also known as transition state, okay, transition state. So the energy required for the above twist and break, so you need to break and then you need to twist, is the activation energy, okay. So once the CN bond is broken, which is this one, the N triple bond C portion can continue to rotate, forming the CC bond, which is this product, the final product. Okay, the reaction explained in terms of graph will be something like this. Okay, you have the starting material. So the graph is basically energy versus reaction pathway. Okay, so the starting material, which is this one. Okay, this is the starting material, and then what happened is basically the N triple bond C will start to bend, and this C N bond will try to break loose. Okay, but the energy required is the what we call is activation energy. So at the top over here, so once it has enough energy, the C triple bond N will break. Okay, so now it straight away become this perpendicular, also known as activated complex. And then finally, it will form the product in which that the CC bond, instead of from the ilium, C bonded to the nitrogen. And if you notice, the energy level of the product, okay, which is this one, the product and the reactant is at different level. The product has lower energy compared to the uh, starting material or the reactant. Okay, from this actually we can tell whether the reaction is exothermic or endothermic, which we will see in a minute later. So the change in energy, which is the delta E for the reaction, is the difference in energy between both reactant and the product. So the activation energy is the difference in energy between reactants and the transition state. So EA is the value of difference in terms of the energy level of the transition state and also the starting material. Okay, so that is the value of EA, while delta E will be the value of energy difference between the product, okay, the product and also the reactant. So the rate of the reaction will depend on this value of activation energy, EA. If the hill is taller or higher, okay, the activation energy is higher, the reaction rate will become slower. So the reaction will proceed at a very slow pace because it requires a large amount of energy. But if the activation energy is low, okay, then the rate will be faster. Notice that over here, the forward reaction is exothermic while the reverse reaction is endothermic. So how we know whether a reaction is exothermic or endothermic? We look at the position of energy level between the product, okay, the product and also the reactant. For exothermic, okay, normally the delta H value will be negative, okay, negative, while for endo, delta H will be positive because in exothermic reaction, energy will be released, while for endothermic, energy will be absorbed. So if you look over here, the reactant are having larger amount of energy. So that means, okay, this delta E is the difference between reactant and product. So the product actually releases energy. That means that's why it has lower amount of energy compared to the product. While for endo, the position of this product will be higher than the reactant. Okay, there is example of this. Okay, in exothermic reaction, if you look over here, so exothermic, normally the energy level of the product will be lower compared to the reactant, while for endothermic reaction, the energy level for the product is higher because it absorbs energy. So this one absorbs energy, while for exothermic, it release, okay, it release energy. So if in real life reaction, if you are doing real life reaction, for example, an organic reaction, you can actually determine whether the reaction is exothermic or endothermic based on the reaction condition of that reaction. For example, the reaction requires you to have the reaction in an ice bath, meaning that the reaction has to be done at very low temperature. probably around 10 degrees Celsius. So that means the reaction itself, the product will release quite a lot of heat. So we can say that that is exothermic. But for most endothermic reaction, okay, the reaction condition will require you to supply energy in terms of heat. So the reaction has to be heated, probably up to 70 degrees Celsius or maybe up to 100 degrees Celsius. Okay, so that is how in real life experimentation you can actually know whether the reaction is exothermic or endothermic. So the EA, or the activation energy, is the minimum amount of energy required to initiate the chemical reaction. So this is another example of energy diagram for exothermic and endothermic. This one has values. So this is how you calculate the values of EA. So for forward reaction, okay, forward reaction, sorry, this way, okay, reactant and product. The EA here is written as 50 kilojoule. So how does the value is calculated? You calculate EA over here, 200 minus 150. That's how you get 50 kilojoule per mole. While the activation energy for the reverse reaction meaning from product to reactant, so the EA value will be calculated 200, which is this one. This will be EA for reverse reaction. So 200 minus 50. So that's how you get 150 kilojoule per mole. And then delta H will be the difference in terms of energy. So delta H in this case is the difference of energy, 150 minus 50. So negative 100 kilojoule per mole. And the same way, you can also calculate for this endothermic reaction. So you get the value of 300 kilojoule per mole by taking 400 minus 100. Okay, so that's how you get 300. While for the reverse reaction, this way, okay, which is 400 minus 300. So this is the EA for reverse reaction. So that's how you get 100. And then the delta H is product minus reactant. So 300 minus 100, you get positive 200 kilojoule per mole. Okay, temperature versus energy of activation. So what does lower and higher temperature, how does it affect the energy of activation? So here we have a graph of fraction of molecules versus kinetic energy. If you look at the higher temperature, this is the amount of minimum energy needed, okay, for reaction, which is the EA. If you look at a higher temperature, a larger amount of uh, molecules are able to what you call exceed the EA. So meaning that it can form product compared to lower temperature, which is the blue color one. Okay, so the amount probably from this graph could be more than double if you increase the temperature for the reaction. So this can be explained by the Arrhenius equation. Okay, another equation you need to know, which is it is given by K equal to A times exponent negative EA over RT, which is then converted because here we have exponent. So we change the value to natural ln or natural log. Okay, ln K equal to negative EA over RT plus ln A, which is EA is the activation energy for the reaction. Okay, and then R is the gas constant with this value of 8.314. T is the absolute temperature, and A is the frequency factor. So what is this frequency factor? So based on the Arrhenius equation above, so this is how the rate constant of a chemical reaction varies with respect to temperature and also other variables. So we convert it into this ln K from the earlier formula, so that we are able to produce a straight graph. Okay, why we want to produce a straight graph like this? Because we can use this y equal to mx plus b. Then from the m value, we can compare it with the EA. So the EA, or the activation energy for that particular reaction, can also be calculated. So based on this formula, K is equal to rate constant, EA is the activation energy, R is the gas constant, T will be temperature in Kelvin, while A, the frequency factor, is basically a constant indicating how many collisions have the correct orientation in order to get the products intended. So if you plot a graph of ln K, which is this is Y, okay, versus 1 over T, 1 over T will be the X, okay, this 1 over T. So the slope that you get is basically the value of EA over R. Since R is a constant, gas constant, you can actually calculate the value of A. So when K is determined experimentally at several temperatures, EA can be calculated from the slope of a plot of ln K versus 1 over T. So but before you can plot this graph, the value of K has to be obtained earlier. So meaning that you have to do the experiment a few times. First by changing the concentration, and then now to calculate the EA, you have to do it at different temperature as well, okay, in order to obtain the value of activation energy. So another plot, okay, ln A is the intercept and slope is the negative EA over R. So you can actually calculate the value of EA. And to the last part of the unit, which is the catalyst. So catalyst is a substance that is added to a particular reaction to increase the rate of a chemical reaction without itself being consumed. Meaning that if you add 1 mole of that particular catalyst at the start of the reaction, by the time the reaction finish, the catalyst will still remain 1 mole. Okay, it helps in the reaction in some way. Okay, the mechanism will be different, but it is not being consumed. So the function of the catalyst is basically to reduce the activation energy. Okay, if you look at this, uncatalyzed, the EA value is higher, but if you add a catalyst, the EA value will become lower. Thus, a lot more of the reactant may be able to pass the A value and proceed to become the product. So a catalyst is a substance that changes the rate of a chemical reaction without itself undergoing a permanent chemical change in the process. Okay, there are two types of catalysts. One is called a heterogeneous catalyst and another one is homogeneous catalyst. So hetero, it is a catalyst that are having different phases from the reacting molecules, while homogeneous the phase of the catalyst and reactant are the same. Example of uh, hydrogen peroxide over here, it decomposes to become water and oxygen gas. But if you add bromide ion as a catalyst, the decomposition occurs very rapidly in acidic environment, and the mechanism is also basically become different because the reaction has become two parts. Okay, this is part one, and this is the product that you want. So Br minus or bromide is a homogeneous catalyst because it is regenerated at the end of the reaction. So the net reaction is still the same like this one, okay, in which that the bromide ion will remain as a bromide ion at the end of the reaction. So how do a catalyst increase the reaction rate? So generally, it is said by reducing the activation energy, but the catalyst can also operate by increasing the number of these so-called effective collision among the reactant. So catalysts usually provide completely different mechanism. So if you look at the example earlier, the way how the product is formed is totally different than if you do not add the bromide ion. So in the preceding peroxide decomposition example earlier, in the absence of a catalyst, the hydrogen peroxide decomposes directly to become water and oxygen, okay, without forming any other intermediate. It's straight away from the products. But when you add this bromide ion, Br2 will be generated, and this is called as the intermediate, which is this one. Okay, this is the intermediate. But the intermediate also is being converted back to become bromide ion at the end of the reaction. So when a catalyst adds an intermediate, okay, these activation energies for both steps must be lower than the activation energy for the uncatalyzed reaction. So in the graph, you have this, the red colored one is the N-catalyzed reaction. You do not add any bromide, but the blue are having bromide ion added. So you have two mini peaks over one big hill over here. So the first correspond to the formation of this intermediate. Okay, so once the intermediate is formed, it follows with another EA, okay, to form the product intended. Okay, but if you do not add any catalyst, it will straight away go to form the product, but it will become very slow because the EA value is very high. Okay, the EA value will be this one. So another types of catalyst, which is heterogeneous catalyst. So heterogeneous are normally in solid phase, okay, compared with their reactant, which is gases or liquid. So the most common example is the use of catalytic converters in cars. What is catalytic converters in cars? It is available in the exhaust of a car. So, okay, in a car you have exhaust. The big drum on the exhaust actually contain the catalytic converters, in which you have platinum or palladium, in order to make sure that the gas being released are not carbon monoxide, because sometimes especially in old cars, the fuel that is some of the fuel are not being burned properly and they produce carbon monoxide. So carbon monoxide is toxic to the environment. So that is why most cars, I think now all of the cars already have catalytic converters. So how does it function? So the first step is actually adsorption. Okay, adsorption is not the same as in absorption. Okay, adsorption is basically binding of reactant molecules to the surface of the catalyst. Okay, so the absorption occurs due to the high reactivity of atoms or ions on the surface of the solid. Okay, molecules are adsorbed onto the active site on the catalyst surface, while the number of active sites on a given amount of catalyst will depend on the nature of the catalyst and how the catalysts are prepared, and also how the catalyst was treated prior to use. So here example we have ethene, okay, C2H2, C double bond 2H2, and then we want to convert. Yes,
Cannot see the slides.
you cannot see the slide. Dah lama ke?
I think less than a minute.
Sorry. Oh, sorry. Sekejap. One moment. Okay. How about now? Boleh tengok?
Can sir.
Alright. Okay, sorry. Okay, where were we just now? This slide, is it? You all cannot see? I think I stop here. So, where was I? Okay, example over here, we have ethene from C double bond C, supposed to be converted into ethane, C2H6. So in the catalyst used is a solid catalyst, and it is in the form of a metal, which is nickel, palladium, or platinum. So it can be any one of these. So basically the reaction above is an addition reaction. So an addition reaction of alkene or a hydrogenation reaction. So we want to add these two hydrogen to these two carbon by breaking the pi bond in the C double bond C, and then forming a 2 sigma bond, okay, or covalent bond. So first what will happen is the ethylene or the ethene and hydrogen molecules are absorbed onto the active side of the metal surface. So these catalysts are on a flat surface, what we call as a catalyst bed. Okay, a catalyst bed in which that you have a flat surface, but not all of the surface are having catalyst on it. Okay, only a few sites have this nickel or platinum or palladium, and on these so-called catalyst surfaces, okay, what we call as active site, the ethylene, which is the ethene over here, and hydrogen will absorb. Okay, then what will happen is the hydrogen gas bond HH will break, and the hydrogen atoms will migrate about the metal surface and runs into the ethylene molecules on the same surface. Okay, and next the third step will be the hydrogen atom will collide with the ethylene molecule on the surface. So the C pi bond will break, C double bond C pi bond will break, and the CH sigma bond will form. So after the product has been formed, it will dissolve, meaning that it will move away from the surface of the catalyst bed. So when ethylene and hydrogen are absorbed onto the surface, so less energy are required to break the bonds. If it is not absorbed, meaning it is free to move around, because the ethylene is in gas phase, and the hydrogen is also in gas phase. In gas, molecules, if they are positioned very far apart from each other, unless the volume is very small or the pressure is very high. Okay, so in order to increase the chances of collision, we absorb them onto a surface of this catalyst. So this is what it may look like. Okay, so first you have the hydrogen and the ethylene molecule being absorbed to the active site. Okay, the purple color and the yellow color is what you call as the catalyst bed. Okay, once uh, they are absorbed, the hydrogen bonds will break, HH will break first, and then after that it will start to collide with the ethylene, which is also absorbed on the same catalyst bed. And after the product is formed, okay, ethane is formed, then it will be removed from the catalyst bed. It dissolves itself. Okay, so that is how a catalytic converter functions. And then another type of catalyst is enzyme. So this is a biological catalyst which is readily available. You don't need to synthesize or anything. So in fact, in our body also contain enzymes. So enzymes are catalysts in biological system. The substrates will fit into the active site of the enzyme, much like a key fits into a lock. So this is where the lock and key theory is being used, okay, for enzyme and substrate reaction. So you have the enzyme and then the substrates. So this enzyme will only accept that particular substrates only. Okay, it will not accept any other types of molecules simply can come in and then want to absorb to the enzyme. No, it is selective. Okay, it will only do one jobs, and only that kind of substrates can be absorbed to that particular surface area. And then the enzyme will do its jobs and the products will be formed. Okay, and so there are as many as 30,000 enzymes in human body. Okay, even in our mouth also we have amylase. Okay, that is if you eat anything, the amylase enzyme will be the first to start what you call simplified the food that you eat. And then you have in starting in your stomach and then in your what they call duodenum. So there are many other types of enzyme to further reducing all of those complex molecule like carbohydrate, fat, and also protein to become its simplest form. Okay, like in protein, the simplest form of protein will be amino acid. Okay, once you eat anything that contain protein, it will try to make the structure into simpler form as in peptide, or first polypeptide and then into peptide and lastly into amino acid. Okay. So most enzymes are protein molecules with large molecular masses, okay, from 10,000 up to 10,000 to the power of 6 of atomic mass unit. And then It has very specific shapes. Okay, most enzyme catalyze very specific types of reactions, and the substance that undergo reaction at the active site on enzyme are called as substrates. So once a substrate locks into the enzyme, a fast reaction will occur. The products then move away from the enzyme. So only substrates that fit into the enzyme can involve in the reactions. So if a molecule binds tightly to the enzyme, another substrate cannot displace it. So it has to wait its turn. Then the active site is blocked and the catalyst is inhibited. So this is what we call as enzyme inhibitors. So basically, these so-called inhibitors is how some drugs are being designed. Okay, as you know, in most viruses, in bacteria, they contain protein. Okay, for example, like in dengue virus, okay, it has 10 proteins. Okay, we have non-structural and also structural protein like capsid, the envelope protein. And you know that dengue virus does not have any drugs to treat it. Okay, so most research currently are being done in a way to look for anything that can inhibit the function of this protein that is available in the virus itself. Okay, because the virus will only work once, let's say, it goes into our body and it will attack our red blood cell, for example. So it works as the same way as this lock and key. So what we can do is actually to block the area in which that the red blood cell are supposed to lock in. So what we call as an inhibitor. So the virus is still there. It's just that it cannot function normally. So meaning that it become harmless. So that is what we call as viral inhibitors. So that is one way how drugs are being designed. Okay, basically on research level. So many poison also act by binding to the site, blocking the binding of substrates. So the binding can also lead to changes in the enzyme. So enzymes are extremely efficient catalysts. The number of individual catalytic events occurring at an active site per unit is called as the turnover number, meaning how many substrate it can process at that particular active site. So large turnover numbers correspond to very low activation energy values, meaning that if it can process more numbers of substrates, it correlates to having low numbers of low value of activation energy. Okay, the turnover numbers are usually very large. Okay, 10 to the power of 3, which is 1000, up to 10 to the power of 7 per second. Okay, not per minute, but per second. So another example, here, if you look at this, okay, the big structure over here is actually how an enzyme looks like, because enzyme is actually protein, and protein basically is a combination of amino acid. Okay, so this amino acid bind together to form that particular enzyme, and the structure is very we can say very large. Okay, and these substrates, okay, the purple color will only come and absorb to a particular active site. Okay, it won't simply come and go let's say on the top part of the enzyme. No, it will directly go where it is supposed uh, to be how to say processed, okay, to make it into a simpler form, which is the same. Okay, example, another example is this Oswald process. So this is how nitric acid is synthesized. Okay, it requires the use of platinum as catalyst. If you look at this guy over here, this is actually the catalyst bed, which will be put inside a very big tank. Okay, so in this case, they use platinum and rhodium mixture of catalyst. Okay, so the function of the uh, catalyst is basically to reduce the uh, rate of the reaction, reduce the activation energy, thus increasing the rate of the reaction. So it involves uh, 4 ammonia molecule plus oxygen, okay, forming intermediate. Once you have this nitrogen oxide, it will form nitrogen dioxide, and then that nitrogen dioxide will then got mixed into the water to form the nitric acid. Okay, so this catalyst, the platinum catalyst, is an example of heterogeneous because it is solid, and the ammonia and uh, oxygen are in gas form. So this is the catalytic converters, which is in cars. Okay, from the engine, it will go to the exhaust pipe. So if you notice in cars, the exhaust pipe is not just a straight like cylinder metal tube. Okay, it has this so-called like big thing, something like this, because inside here is the where you put the catalytic converters to change any unburned hydrocarbon to become carbon dioxide and water, which is safer to the environment, okay, compared to carbon monoxide. So that is this is some of the reference that I use, okay, and these are the tutorial question as well, which is in the notes. Okay, so this one I think I have shared the question. If it's not in Google Classroom, you guys let me know. I will post. So